Okay, off we go. So real quick before we get into the math, so I've been getting a lot of questions from students about, hey, how come I'm not on the Canvas site, or how come I'm not on the Gradescope site? And the answer is because I have not created them yet. So nothing to worry about. The Gradescope site I will probably create tomorrow or Friday. Certainly plenty of time before the first homework due date. Of course, the first homework due date is Sunday. Right? So anyway, don't worry about it. We will get that taken care of. I like to wait until what you might call the last possible minute because the class roster is in serious flux right now. People adding, dropping, etc. And it just doesn't make sense to create a site and then have to go in and manually fiddle with the roster. It's unnecessary make work. So the Canvas site probably won't create until right before we start attendance quizzes. Attendance quizzes will begin, again, once it makes sense to do so, probably middle or late next week. I will give an announcement, almost certainly an in-class announcement and an email announcement talking about all those details. But again, I'm not going to make that site until the last possible minute. One last thing, and this is in the website, of course, but I will plan is that I will only use Canvas for the attendance quizzes. I'm go so far as to say I'm boycotting Canvas, but I'm opposed to Canvas. But it does have this one capability that's very handy. Okay, so. Hopefully that'll address a lot of those concerns. So off we go, picking up where we left off. We were talking about parametrizing curves. In other words, how to create a parameterization of a curve. Not how to interpret an existing parameterization. We did several of those. But how do you create a parameterization? And again, it's a bag of tricks kind of thing, right? Tools for your toolbox. So here's another cool tool. Vector algebra. Really useful, as it turns out. So this is the underlying point in this example we're about to talk through. Let's suppose I have a wheel like so, and it's rolling, like so, right? And turning as it's moving, of course. That's how rolling works, right? The x-axis is the ground, as it were. And so, with this in mind, looking at a reflector attached to the edge of the wheel, that's where they put a lot of bicycle reflectors, kind of as close as they can get anyway to the edge. That's going to trace out some sort of a weird path like this. That's going to kind of do like so. Y'all have probably seen this, right? Especially at night. Dusk or whatever, and somebody's riding a bicycle by, and that reflector does this weird scallopy kind of pattern. That's the curve we're going to parameterize. Weird curve, right? Side note: it turns out it's extremely difficult to find an equation for this curve, right? And it's tempting to say, "Oh well, golly, equations go." I've been doing equations forever. If I can't even find an equation, how on earth are we going to parameterize? Turns out parameterizing is a lot easier. Hard to predict, but that's the case. Okay, so we're going to look at where that reflector is at a given moment, and here's the big idea. Here's where arguably the big lesson is just the following point. That point where the reflector is easily understood as being a sum of the location of the axle, which of course keep in mind you can think of that as a position vector, whatever. The axle plus this, what I'm going to call a spoke, if you will. Right, but this little displacement, from the center of the wheel to the edge of the wheel where the reflector is. So blue plus purple is orange. Now I claim that's that almost by definition of D, right? D being the difference, of course, when you add. It's obvious, right? What's really nice about this is it's going to turn out to be really easy to understand the motion of the axle, and it's going to be not that bad, not that much trouble to understand how this purple vector changes. And so basically what we've done here is we've taken, let's see here, let me go back back into this mode. We have taken what I'm going to call a hard problem, and we've turned it into a sum of an easy problem and another easy problem. And sometimes that's how things work out when you break something up into pieces. Sometimes the whole is not the sum of the parts, right? When you're talking about difficulty, sometimes the whole is way harder, and the sum of the parts is actually not that bad. Okay. All right, so let's talk through some of the details. Now, this is all written down in the notes, times a factor, tough choices, and all that. We've talked about that before. So I'm going to go kind of quickly through this, but I think this is all pretty reasonable. Let's talk about the axle first. Here's the axle. The axle, of course, is just going to move in a straight line. Sweet. Nothing to it. A couple of details. Let's think through the details. The thing that's going to, here's an easy one. The low-lying fruit on this is the height is clearly always going to be the radius, right? So let's go ahead and note that. The y-coordinate, the constant a, no big. Okay. All right, what's the x-coordinate? Well, we're going to need to understand the x-coordinate as being a function of something. Right, that's the whole idea of parameterization. Position is a function of a parameter. I'm going to use t as the parameter. We have to decide what should t be, right? How are we going to choose t? We have a lot of options. I'm going to make a choice that I think is very convenient. By the way, when you make your choices, when you're parameterizing stuff, think carefully about your choice of parameter. Right? And try to make a choice that's going to be both natural and convenient, or some reasonable compromise between the two. And here's what I like about this choice of t that I have right here, calling it that angle, is that when we start at the very beginning, that angle over here, 0. That's natural. That's convenient. Right? And as the wheel rolls, as time passes, right, that angle t increases as time does. Right. So now, reasonable complaint. How does this factor in the speed of the wheel? Importantly, I don't really want to think of t as being time. T is just a parameter, right? And in some practical circumstance, if you really do need to know how the motion relates to time specifically, then you'd have to worry about speed, and it's an extra constant you'd have to throw in. We're not in that circumstance. I just want any parameterization, so I'm going to ignore the speed issue. I'm just going to call that angle t. That's our parameter. It's not time. No problem. Okay. So that choice having been made, here's the first super convenient insight, and that is when a wheel, actually before I write it down, when a wheel is rolling along the road, it doesn't slip, hopefully, right? Presumably. So what does that mean, not slipping? How would I represent that? And I think a pretty reasonable way to do it is like this. The amount of road that has touched rubber needs to equal, color choices, needs to equal to the amount of rubber that has touched a road. Now that's a physical appeal, right? I can't prove that, but I think that is a plausible suggestion. Does that make sense to everybody? Everybody, you willing to believe the amount of rubber that touches road is the same as the amount of road that touches rubber? So cool. Well, here's the thing. The x-coordinate of this point that we're looking at, that x-coordinate is the amount of road that has touched rubber as of this moment. And the amount of road, if that's equal to the amount of rubber, we'll check out the rubber. The rubber is an arc of a circle whose central angle I know. Right? And pretty easy to persuade yourself that the radius is a and the angle is t, and so the arc of a circle is that product A times T. Flashbacks to high school geometry. Hope everybody remembers all that stuff. Everybody good? Okay, all right. Next part of the problem. We got to worry about this vector here. How are we going to understand this vector? Common mistake. A lot of students misunderstand and think that what that vector is doing as the wheel rolls, that vector is doing this, right? That it's rotating and that it's moving. And that's not true. It's a fundamental misunderstanding of what a vector is. A vector is a direction and a magnitude. Notice I didn't say location. Right? Vectors don't have locations. That vector that we're interested in is exactly the same as that vector, which is exactly the same as that vector. Same direction, same magnitude, same vector. It's a shortcoming of our drawing tools that we represent vectors with arrows. Arrows are a nearly perfect tool for representing vectors, but they're not perfect. They're nearly perfect because they have a direction, they have a magnitude. Unfortunately, they have location. See, I drew this arrow right there. It has a location. There it is. Right? But the vector doesn't. So this is something you have to remember when you're thinking about a vector. We will draw it with a location just because that's how drawing works. It's not because that has anything to do with the vector itself. Vectors don't have locations. Okay, so keeping that in mind, a much easier way to think about that vector is to put its tail at the origin, like so. Right? And now if I want to know the location of the head of that vector, where's the head of that vector? Oh, well, that's no problem. That's, boom, right there. A cosine theta, A sine theta, basic trig. Everybody good with the basic trig? If you're not good with the basic trig, make sure that you polish up those skills. Right? It's going to be assumed. So there you go. Here's the problem with what I've written down. I've written that D vector. Oh, you know what? Okay. This should be red. Sorry. Try to be consistent with the colors. There we go. Okay. We need to write everything in terms of one parameter. We've already decided our parameter is going to be t. I wrote down this equation because it was easy, because I understand how that vector relates to this, the usual theta angle, right? So it was easy to write that down, but I do have to write everything in terms of one parameter. Again, we've decided that's t. So I have to make the following slick observation, which is that the angle t, which goes like that, and the angle theta that goes like this, those angles always add up to 3 pi over 2. You can think of it this way: as time passes, right, as t increases, as this thing rotates clockwise, t is going to be increasing, theta will be decreasing by the exact same amount. Everybody on board? Yes.
So t is how much the wheel is turned, basically the angle.
Yes.
And so
that's right.
So theta would be like the, I guess, difference between where it is and the ground.
Yeah, sure. You can think of it that way. The way I'm proposing to think about it here is just that it's a familiar thing. It's this, back when we did trig, we arbitrarily decided that theta would be this angle as measured from the positive part of the x-axis. And so that's really what I'm just trying to get a hold of. The whole reason I brought up theta in the first place is so I could invoke familiar trig formulas. Yeah. Is that cool?
Yeah, thank you.
Yeah. Yes?
Why do they have to add up to 3 pi over 2, not...
Because of how I arbitrarily set up t, basically, right? So t starts down here. T is 0, like here, right? Here theta is 3 pi over 2, and t is 0. And then as as time marches on, the sum remains constant. So, yeah. Okay, so what? Why did we bother with this? Oh yeah, that's right. We need to rewrite everything in terms of t. And so the way we rewrite everything in terms of t is that we take this formula for theta, we plug it in for those thetas in the convenient formula we'd already written down. And when you plug that in, you're going to find you're going to be looking at cosine and sine of a sum. And so you're going to be like, oh my gosh, those angle addition formulas that I saw in high school trig class, what happened to those? Where do I find those formulas? I just want to point out, this is one of the things, you'll probably remember this explicitly on the content syllabus. I do require that everybody know those two formulas, the angle addition formulas for sine and cosine. Just sine and cosine, don't worry about cosecant. Don't care. But we do need to know those formulas, and when you do that, the punchline is that this red vector we're interested in turns into that. So make sure you can do that. There's some blanks that I left that you want to make sure you fill in those blanks for that last bit. And it's all over but the shouting at this point then. Let's see, let me try to get as much of this on the screen as possible. So as we saw initially, the location of the reflector that follows the path that we're interested in, it's the sum of where is the axle. Oh yeah, cool, we found the axle. That's what the axle is. Plus the plus this, I think we used purple for this, plus this spoke vector, D, that we just figured out there, and vector algebra, purple plus blue is orange. Everybody see what happened there? But there's a bunch of little details. This is a great example, by the way, of a sort of a larger strategic kind of psychological point, which is there will always be details. It is possible to get lost in the details. You want to make sure to periodically step back and remind yourself what is the big picture of what's going on here. So yeah, there's little details to worry about. If y'all want to ask me about some of these details in office hours, right after class, conveniently, or what have you, fine, of course, no problem. The big picture point is that this thing that we didn't know how to get our hands on, we were able to get our hands on it by realizing it as a sum of simpler things by way of vector addition. So, very often a good thing. Okay, moving along. Another example, we're going to use the same tool here, and we're going to figure out how to parameterize a line. So how do I parameterize a line? What line, you ask? Okay. Oh, well, I guess I better describe the line. Okay, so we're going to say it's the line that goes through that point and that's parallel to that vector. And easy observation: there is a unique vector. There is a unique line that's described by a given point in a given direction vector. Does that make sense? Okay, so how to parameterize this line? Well, I need to tell you how to generate points on that line. In other words, I need to find how to write points on that line in terms of some parameter. And here's how we're going to do it. It's not hard to persuade yourself, I think, that what we're talking about is that vector, R0, plus this vector, and we've got to be a little bit more careful, this blue vector was not given. But look at that, it's a scalar multiple of something we were given. So I'm just going to let t be that scalar. And now, as desired, I have position r as a function of one parameter, t. And of course the givens, right? R0 and v were givens. So How we doing? Everybody all right? You want to make sure you are really good with this example, and make sure to remember this construction. Parametrizing lines is going to come up countless times. So you want to be ready. You want to have that, shoot from the hip, ready to go as needed. All right. Moving along. Here again, we've talked about this before, but this kind of thing is going to come up. I usually will say something or another about what we're not covering, but this is an indication I don't really have time to talk about all of this, and again, I wish I did. If we had 300 minutes a week instead of 150 minutes a week, I would do all of it and more, right? But we just don't have the time. So make sure to read this. I think this example is pretty straightforward, so make sure to give that a read. Hope you'll find it instructive. I do want to say a couple of words about this stuff here. And that is the difference between equations and parameterizations. Right? We've talked about parameterizations. We've talked about equations. When you write down a parameterization, the way you write it down is with an equal sign, right? So technically a parameterization is kind of an equation, at least in terms of how we write it down. But it's got a very different sort of relationship with what it's describing. If you're describing a curve with a parameterization versus if you're describing a curve with an equation, super different. In particular, parameterizations produce points on the curve. You put in some arbitrary value of the parameter, and it literally constructs a point on the curve for you. So it's what I like to call a point generator, right, with that in mind. That's not what equations do. Totally different thing, right? You can't plug parameters into an equation. There is no parameter in the equation, right? It's just not that. It's a totally different critter. So equations, what I like to call point testers, in the sense that if you have some point that you think may be on the curve, you want to decide if it's on the curve or not, plug it in, and the equation will either give you a yay or a nay, right? If the equation works, yes, that's a point on your curve. If the equation does not work, then nope, that is not a point on your curve. It's literally testing points. Is that cool? Everybody with me? So that's a big difference, right? Let's take a moment to recognize that a point tester and a point generator, these are, these are importantly different things. Okay, so make sure to keep that in mind. By the way, there is a common term for parameterizations. I can't remember if I said this last time, but a common alternative term for a parameterization is parametric equations. I think this is terrible terminology. Oh my God, it blows my mind. There are these two things that relate to curves in such different ways, right? They're fundamentally different things. When you're trying to distinguish things, don't use the same word to describe both of them. I think that's really unfortunate, right? So anyway, heads up for that. When you see something called a parametric equation, it's just an unfortunate term for a parameterization. And I encourage y'all to try to lean toward the term parameterization. Okay. Another example. This example sort of explicitly uses both of these features of both of these constructions. Right. So I think this is a really nice example. Give it a look-see. It's pretty readable, I think. Again, as with all of these, when I say something for y'all to read, I'm very happy to discuss in office hours. Come on into office hours. We'll talk about it. Happy to. No problem. Okay. All right. What about in 3 dimensions? Well, in 3 dimensions, Very easy to parameterize stuff. It's pretty much the same. Parameterizing in 3 space, not that different from parameterizing in 2 space. For example, here's how you parameterize a line in 3 dimensions. Again, if there's a starting point plus parameter times a direction vector. It's exactly same idea. All right. So what if I wanted... Okay, I'm going to say this deliberately wrong first. What if I wanted an equation of a line in R3? Okay, well, you can. Probably, technically you can, but it's obscure and useless. But basically, an equation in 3 space you would expect to be a surface. Again, we'll talk about that more later. But a surface is not a line, so an equation you just can't really expect to work. But can we still, maybe, possibly, we might be able to find a point tester in some way, right? The parameterization generates points. Sometimes still, though, I might want to test points and get that yay or nay. So how does that work? So I'm going to start off with a silly observation. If you come to me with a point, and you say, okay, test this point for me. I got a point x comma what? By the way, we're going to presume that the starting point and the direction vector are all given. Okay. So given a particular line, you come to me with a point and you say, hey, is that point on the line? The silly answer is, well, I would need to decide if there is some value of t that makes that equation work. And I say that's a silly answer because how am I supposed to know? Right? Am I going to solve for t? Or how do I decide if there is or is not a t? And a quick digression, I want to recognize that not everybody knows these symbols. Let me just get rid of all this. This symbol here is just a little shorthand. It just means there is or there exists. And this little symbol right here means such that or so that. So all this statement says is, if you want to know if a point is on a line, you need to know, does there exist some value t such that when you plug that t in, you generate the point that you're asking about. Okay. So kind of useless, but we can sort of make use out of it as follows. Clever move coming up. Don't forget, this is actually 3 equations. That's a vector equation, right? But that means it's actually 3 separate coordinate equations. You could write this out at, x equals x naught plus ta, right? Y equals y naught plus tb, etc. Right? This is 3 scalar equations. And in those 3 scalar equations, you can solve for t. That's what you get in the first equation. That's what you get in the second equation. And that's what you get in the third equation. So let's just go ahead and write that down. And hardly anything really happened there. So yeah, again, we have this seemingly unanswerable question. How do I decide if there is or is not a t that makes this equation work? I don't know. But how do I decide if there is or is not a value of t that makes all 3 of these equations work? This is actually a really easy question. If I need t to be this, and this, and this, I need t to be 3 different things? Wait, t can't be 3 different things, right? The only way t can be 3 things is if they are not different. The only way it can happen is if these 3 things are all equal to each other. If these 3 things are all equal to each other, then, is there a value of t equal to all of them? Why, yes, there is. Whatever that value is, that's the t that's equal to all 3 of those things. And if this fails, if any 2 of these expressions are different, Any two. Anything other than complete agreement. Well, then you're trying to get t to simultaneously equal to 7 and 12. It's not going to happen. Does that make sense? All right. So it's weird how sometimes a subtle little rephrase turns seemingly useless observation into the perfect observation. And this is our point tester right there. Given the starting point and the direction vector, you write this down, you give me a point x, y, z, you plug in and compute all three of these things. They're all the same, that's a point on your line. If they're not all the same, then it is not a point on your line. Okay, and this is called the symmetric equations. Symmetric equations for a line. Is everybody happy? Okay, so that's section 1.2. Moving along now to 1.3. Let's see here. A lot of this is review. In fact, the great majority of what I wrote down for section 1.3 is in one of these boxes that says for students to read, because y'all have all had a course in linear algebra. You should know what the dot product. I feel very confident that you know what a dot product is, or that you should know what a dot product is. As usual, if you're not comfortable with any of this stuff, come talk to me. I'm very happy to help, right? Just come to office hours, walk you through whatever might be needed. But presumably you've seen that formula dot product. You know there's a bunch of properties. They're in the book. Read all that. Okay. And I think it's a really good observation just to remind you that inner products. Now y'all may, or I think y'all have seen inner products. Show of hands, inner products? Good, okay. Inner products, very, very powerful idea. Like, really, really powerful. Do y'all know the one about wavelets? You probably don't know the one about wavelets. So, y'all know Fourier series. Okay, the big idea of Fourier series is that you can write a complicated function as a sum of simpler functions, namely sine waves. Wavelets are going to do something very, very similar. We're going to try to represent a complicated function as a sum of simpler functions. It's just a different kind of function. And these simpler functions can be used, for example, to do image compression. It's really wild. It's hard to see it coming, but it's just a different collection of functions. How does all this work? I don't know if y'all have seen the following point of view on Fourier series, but those coefficients, the Fourier coefficients, are inner products. Right? Like with, y'all will remember from linear algebra class that if you have some vector and you want to write that vector as a linear combination of some orthonormal basis, you use dot products. Dot products will give you those coefficients. It's got to be an orthonormal basis, but dot products will give you the coefficients. Wavelets are an orthonormal basis in the inner product space, right? That uses a special inner product, and you compute the coefficients. You compute the wavelet coefficients by inner products. And so you take a complicated function like a photograph, which you can think of as a function in a certain way, do a wavelet breakdown on it, you write it as a sum of these very much simpler things, and all you have to do is record the coefficients, and image compression happens. It's a very powerful idea. Okay. Ultimately, all from inner products, ultimately all motivated by dot products. So, all right. Okay, I do want to say a couple of words about these terms. I have heard many times these words used interchangeably. I've done it, unfortunately, a few times myself. I was, as I like to say, I wasn't brought up right on this point. These are different ideas. They're very commonly overlapping. Very commonly, vectors that are orthogonal are also perpendicular, and vice versa. right? But they are different ideas. They refer to different things. And I think the distinction is really important. In particular, now y'all probably remember the definition of orthogonal. It's a purely algebraic definition. Two vectors are orthogonal if the dot product is 0, right? Remember that? Okay. It would be a misstatement to say that this is a definition of perpendicular. It's not. Definition of perpendicular. Perpendicular is a geometric idea. Perpendicular is about vectors, and you look at the directions that those vectors point, and you look at the angle between those two directions, and then you see if that angle is a right angle. That's what perpendicular means. Notice it's all geometric. Directions and angles. It's all geometry. So they're fundamentally different in that sense. The really sticky point is that this geometric idea, the idea of perpendicularity, requires that there be an angle, which requires that the vectors have directions, which requires that the vectors not be 0. It doesn't make any sense to talk about 0 being perpendicular to something. It doesn't have an unambiguously defined direction. So what does it even mean? What direction are you talking about? Right? You can't make any sense out of perpendicularity with the 0 vector. Only works for non-zero vectors. No such issue for orthogonality. Dot product can be 0. No sweat. In fact, conveniently, when one of these vectors is a 0 vector, the dot product must be 0. So it's important that we keep these ideas distinct. Sometimes you need one of them and the other one will not do, and vice versa. So I'm a big fan of keeping these terms distinct. I try my best, but again, I wasn't brought up right. I was brought up mathematically, using these as being basically the same thing, and I've been working on it. I'm getting pretty good at it at this point, but y'all are much younger than I was when I started to realize, oh my gosh, how embarrassing, right? And so hopefully y'all can break this bad habit before you really develop it too terribly strongly. Okay. All right. Okay, so let's talk about, again, briefly. Right, so y'all should make sure to read all this stuff. You may have seen this stuff before. Here's how to make a unit vector out of any vector. Divided by its own magnitude. It'll always give you the unique unit vector pointing in that same direction. Extremely commonly used formula. Make sure to be good with this. Make sure to understand why it works. Obviously, make sure to know the formula. And then we're going to talk about this thing called a component. I'm not going to go through the algebra. It's an easy read. Y'all can totally do that. But let's talk about the picture. The idea of a component is that if you have a direction, if that's the direction that you're interested in for whatever reason, and my favorite little metaphor here is to think about playing football, and if the ball is here, and then the play happens, and then the tackle is made there, how many yards were gained? Is it this many yards? No. Right? No, definitely not. Right? You only get credit for how the ball moves downfield. To whatever extent, in other words, the ball has moved in the given direction. So this is called the component. Is that cool? Everybody on board? Could be negative, right? If the quarterback is sacked and this is the displacement of the football, right? Something like this. Well, that's a loss, and the component should be negative. Okay, so it's tempting, all too tempting. And again, I'm going to make this mistake as well. It's tempting to call this a distance. Right? It looks like a distance as drawn in this picture. It feels like a distance. It's just that it can't be. The word distance is an intrinsically positive thing. Right? And it's annoying and fussy, but really important distinction. Right? So you can call this a scalar. That's cool. You can call it a coordinate. Perfectly fine. technically not a distance. Disallows negatives. Okay, so how you compute that component, this is the part I'm going to have y'all read. Basically, this is just the trigonometry of that triangle, no big deal. Take a look, make sure you're good, manipulate the algebra, blah, blah, blah. What you will find is that that component is computed by that formula right there. Okay, so make sure to know that formula. Make sure you understand that derivation, right? Again, just because I'm not going to cover it doesn't mean you should know it. But that's what the punchline is. I like to make the observation that that right there is a unit vector. All right? And so components then, right, the component that we were just looking at, components are dot products with unit vectors. I think that's a really nice way to think about it. So arguably you got in some sense, two choices here, two different ways you can compute a component. A lot of people like this formula because it is really pluggy-chuggy, right? I mean, you give me a V and a W, boom, plug and chug. That has an appeal. Don't forget, that's answers, not ideas kind of thinking, right? So I've gone on at length. I'm not going to do that whole spiel again, but we are here for ideas. That's what's most important here. And the idea, why is this formula true? Well, there's a long story there, right? Why do you divide by the magnitude? Okay, well, trig, blah, blah, blah. There's something really nice, though, about this formula. It just rolls off the tongue very nicely. Components of dot products with unit vectors. Right? It's very crisp. It's easy to remember in that sense, if nothing else. Right? But a case I would make is why a unit vector? Well, the only reason I was interested in V in the first place is I needed some way to describe the direction I cared about. The direction is all that matters. That's what defines component. Component is defined by taking your vector, whatever the vector is, and looking at how much in a given direction. So whether I describe that direction by one vector or a different vector or a third vector, which of these dark green vectors should I use? Doesn't matter. The magnitude is a distraction, right? It's only the direction that counts. So I think this formula here is, okay, it's fine if you want to memorize it. Okay, go ahead, right? But I think this is really the more natural equation. Okay. Next, talk about projections. And again, details to read. I'm going to say a couple of quick words. Try to be quick. Oh my God, is it really already? Good Lord. Okay, I'll try to be quick as I can. You'll recognize this picture. It looks like the exact same picture from the previous page. The only difference is that instead of being interested in the scalar, again, you're going to want to say distance. Instead of being interested in the scalar, we're interested now in the actual vector itself. The vector is what the projection is. So that's the important distinction between components and projections. Components are scalars. Projections are vectors. Everybody see the difference? Sometimes you need one, sometimes you need the other. So we have to have both ideas. Very conveniently, we can understand a vector by its direction and its magnitude, and well, it's pretty straightforward to see that the unit vector gives you the direction, and of course the component is the magnitude. So real easy little formula to remember there. And then, by the way, to be clear, we already have a formula for components, and that makes for a very compact little formula there for how to compute projections. This is my favorite formula for how to compute a projection. Let's see here, I'll do it like this. favorite formula. Now, if you look in the book, you will notice they push that formula. And again, you have this kind of like, pros and cons. Which one do we like better? And again, this one is pluggy chuggy, and there is that appeal, right? But why the dot product of the two V's in the denominator? Where does this come from? The intuition's a little cryptic immediately, right? I think the intuition here is super easy. This is the magnitude, this is the direction. That's why, right? This one, easy connection to ideas. So conceptually, I think this is the better formula. And yeah, okay, sure, computationally, I have to compute the U vector first, okay? And fine, I suppose you could use this if computation was your goal. But again, computation is tip of the iceberg. We're mostly going to be interested in ideas in this class. So I really do think this is the better formula up here. Okay, so that's 1.3. On to 1.4. No way we're going to finish this in 4 minutes, but I do want to get the ball rolling. Y'all know what a vector is. I'm going to just talk about something called a list of vectors. A list is kind of like a set with a one big difference. A list is ordered. Which one's first matters. So when I say the list A comma B, I don't just mean the pair of vectors A and B. I mean the pair of vectors with the understanding that A is first, B is second. There is also the list B comma A, I suppose. That's not the list I'm going to be interested in, whatever. Okay, so the order matters. All right, so notice if you have two vectors in R2, the first vector perhaps might be something like that. The second vector, I suppose, could be something like that. And notice now, keeping in mind the order, A is first, B is second, suggests what you might call counterclockwise for that list. Everybody see what I mean there? If I think of A is first and B is second, and like in some sense, as you go from A to B, you have to kind of rotate yourself counterclockwise for as drawn there. Now, of course, it could be maybe that's what A could be. I don't know, whatever. Maybe this could be what B is. Now, same list, A comma B, or excuse me, A first, B second. But notice now, because of this choice of actual vectors, now that suggests clockwise. So this is what I mean by the geometric order of a list. When you have vectors, let's say these, when you write down one of them first and one of them second, that suggests generically either counterclockwise or clockwise. Is that cool? Okay, but there's annoying third examples. Sometimes they're parallel. That's neither clockwise nor counterclockwise. Sometimes they could be opposites. Again, it's kind of neither clockwise nor counterclockwise. What if one of the vectors was the zero vector? Various annoying anomalous cases. Here's the good news. It is exactly the cases in which the pair is linearly dependent. So what we really have here is kind of a trio of possibilities: counterclockwise, clockwise, or dependent. And every list of two vectors in R2 is exactly one of those three things. Is that cool? No surprise, counterclockwise is the mirror image of clockwise. Right? No surprise there. I hope no surprise if you sort of trade the positions. If you take the one that was first and you make it second, the one that was second you make it first. If you switch two of the vectors, that'll always switch the order, right? Let's see here. Let me do the picture here. A first, B second, counterclockwise. B first, A second, clockwise. Excuse me. Okay. And then last observation, this is all independent of rotation, and so, the hands on my watch turn clockwise. If I rotate my watch like this, they still turn clockwise, right? It's just whatever. Rotation does not affect the order of a list of vectors. Okay, so that's all pretty intuitive, I think. And I guess I have to recognize we're out of time. So we will draw the line right here, and next time we'll do a three-dimensional version of clockwise, counterclockwise, and take it from there. Y'all have a good one. See you later.